Okay.
Okay. Well, hi everyone, and welcome to this second webinar titled Functional Recovery Qualification Procedure for Seismic Force Resisting Systems. I want to start by thanking Fabio and also Damien for the invitation to share this work. As you heard, my name is Carlos Molina Hutt, and I'm an associate professor of structural and earthquake engineering at the University of British Columbia. And I'm also a member of the Resilient Design Coalition, or RDC. The Resilient Design Coalition was founded just over a year ago to advance resilient design within the structural engineering community, with an immediate focus on developing seismic design provisions for functional recovery performance. So this work directly supports the upcoming 2026 NEHR provisions and the ASC 728 standard. So this coalition brings together folks from HB Risk, KPFF, and the University of British Columbia, and you can see the logos in the bottom right of the slide. And our work is supported by the Charles Pankow Foundation, along with a broad group of industry partners. So the goal of today's presentation is to give you an overview of this standardized procedure for qualifying seismic force resisting systems for functional recovery performance, which will be included in the upcoming Appendix A of the 2026 NEHRP provisions. So before I get started with the presentation, I'll briefly introduce my research group, even though Fabio already said a few words about this. So my research group is called the Engineering for Seismic Resilience Laboratory, or ESR Lab. And our work focuses primarily on quantifying seismic risk in buildings and infrastructure and its implications on urban resilience. So we try to develop tools and data that can be used by practicing structural engineers, but also seismic planners and policymakers. And the work that I'll be sharing in today's presentation feeds directly into the building code, at least in the US. But we also have work that we do more on a regional scale type of assessment with it's something that we do in partnership with municipalities to try and inform seismic policy development. So this is the composition of my research group. I have currently one postdoc and four PhD students. Our little helper whiskey in the bottom right. And in today's presentation, I'm going to highlight the work of a former student, Kristen Blows. She finished her PhD here at UBC within the past 6 months or so. And she's now a postdoc with Abby Lyle at the University of Colorado Boulder. And then also contributions from Hui Pam, a former PhD student at the University of California, Berkeley, and now a postdoc here at UBC. So there will be three parts to this webinar. I'll spend a few minutes giving you an overview of the structural and non-structural design requirements for functional recovery performance that you'll find in Appendix A of the upcoming 2026 NEHR provisions. This will serve as the point of departure for the qualification procedure, which I'll explain in part two. And in that part, I'll focus primarily on the general methodology. And then in part three, I'll spend around 20 minutes walking you through an illustrative example to help convey the method. And I'll provide also a summary of our results for a wide range of systems that the Resilient Design Coalition has worked on qualifying over the past few months. So for context, in the US, seismic design provisions are vetted through two consensus-based processes. The first one is the Building Seismic Safety Council's Provisions Update Committee. So I'll refer to this Provision Update Committee, or PUC, throughout my presentation. And they generate the NEHRP recommended seismic provisions. And then after that, AAC 7 committees take the material that NEHRP has put forward, and then they further refine it for inclusion in the AAC 7 standard. So the image on the right shows the cover of the last NEHRP provisions, which were published in 2020, and those served as the basis for seismic design requirements that you find in AAC 722. Now we're just finalizing the 2026 NEHRP provisions, which serve as the foundation of seismic design requirements in AAC 728. So that's sort of the big picture context of where you're going to find a lot of what I'm sharing with you today. Okay, so I'll start by providing a high-level overview of the prescriptive design requirements for functional recovery performance that you will find in this upcoming Appendix A of the 2026 NEHRP provisions. So I want to share 5 key points that you can see in this diagram. The first one is that buildings designed for functional recovery performance are assigned a functional recovery category ranging from A to D based on the intended function or service that that building provides to the community. And each recovery category has a target recovery time, which can go anywhere from 0 hours for functional recovery category A to 6 months for functional recovery category D. The second point relates to the ground motion hazard used for functional recovery design, which is the functional recovery earthquake, or FRER. And it is a risk-based characterization of the earthquake hazard, which is generally lower than the design earthquake, though this varies from site to site within the US as a result of this, risk-based approach. So the risk target associated with the functional recovery earthquake is to have a 10% chance of exceeding a recovery time target in 50 years. And the associated reliability target is to have a probability of 25% or less chance of exceeding recovery time targets conditioned on the occurrence of the functional recovery earthquake ground motions. So these first 2 points that I highlighted are integral to the development of prescriptive design provisions for both structural and non-structural systems, because the provisions aim to ensure that we meet these recovery targets, which we verified by using the ATC 138 framework, which is a framework to quantify functional recovery time in buildings. So as you'll hear later in the presentation, for functional recovery categories A, B, and C, we allocate 10% of this 25% reliability target to the structural system and the remaining 15% to non-structural systems. So we can develop essentially distinct structural and non-structural design requirements. Now, on the structural side, we've done this by introducing a response modification coefficient for functional recovery, RFR, and allowable drift limits for functional recovery performance, delta A FR. And on the non-structural side, we've introduced seismic functional recovery component importance factors, or IPFR, as well as seismic qualification of equipment that is required to support the building's basic intended function. So a lot of this is trying to mirror, the current approach in life safety design, essentially to ease implementation of these new design requirements. Last but not least, at the bottom of the side, we have numerous QAQC requirements that really help ensure that all of this comes together. And I'm going to share a few more details about the structural and non-structural system design before jumping over to the qualification procedure. So there are a couple key points that I want to share with you about our approach to developing prescriptive design requirements for structural system design. The first one is that the lateral force resisting system is designed to have reduced ductility demands, and this is achieved by means of a reduced response modification coefficient, this RFR term that I just alluded to. And that variable depends on the functional recovery category, and it's of course system specific, like the R value that we typically find in life safety design. The second point is that allowable story drift limits are going to range anywhere from 0.75% to 1.5%. They're also going to depend on the functional recovery category, and they're going to be system specific, which is a key distinction from life safety design, where we typically have a single drift limit for all systems. Right now, we're providing drift limits that are system specific. We consider damage to structural components only when we're exploring appropriate values of RFR and drift limits, and we use safety critical structural damage as our building level performance metric. Safety critical structural damage is structural damage that must be repaired before a building can be reoccupied. And the key idea here is that a structure that is deemed safe is essentially a first requirement for recovery. And also that safety critical structural damage is essentially a proxy for very lengthy recovery times, which is exactly what we're trying to avoid with these provisions. So by exploring a vast assigned space of RFR and drift limits, we can then select values that are going to minimize the probability of safety critical structural damage on a system per system basis. All of this, of course, conditioned on the functional recovery earthquake. And essentially what we're doing is targeting a 10% or less probability of safety critical structural damage for functional recovery categories A, B, and C, and slightly relaxed values for functional recovery category D. Since the notion of safety critical structural damage is integral to this work, I want to go over this concept with you because it's possible that you haven't heard of this before. So in our analysis, safety critical structural damage aggregates component level damage to a building level performance metric, and it captures whether there's been a substantial loss of vertical or lateral load carrying capacity. Now, this building level metric considers the distribution and the severity of damage throughout the structure. And to calculate the probability of safety critical damage, we use the fault tree that you can see on the right hand side of the slide. And you can see in that diagram, the fault tree has three main branches that are evaluated to determine whether there's been safety critical structural damage in the building. So on the left side, structural components are going to be surveyed on every story to determine whether the structural system is unsafe. So if safety critical damage occurs in any story, then the building is deemed unsafe to reoccupy. And the severity of component damage is expressed in terms of safety class. And this is essentially done by mapping damage states in different components to corresponding safety classes. So for instance, a safety class of 1 includes moderate damage that doesn't cause the loss of lateral load carrying capacity. A safety class of 2 includes severe damage that does result in the loss of lateral load carrying capacity. And a safety class of 3 includes severe damage that leads to both the loss of lateral and gravity load carrying capacity in the component. So the more severe the safety class, the lower the percentage of components that we can tolerate before triggering safety critical structural damage. Now, of course, collapse or excessive residual drifts would also lead to safety critical structural damage, but collapse in particular is mostly irrelevant in our study because we're dealing with systems that at minimum meet life safety requirements. We're looking at new buildings. However, residual drifts is something that does need to be considered, and for some systems it's not an issue, and for others it could be of significant impact. I also wanted to share relevant considerations for non-structural system design. So a central concept is the seismic floor acceleration demand. This is not typically captured in conventional structural analysis. So we're using FPFR, which is analogous to FP in AAC 7, Chapter 13. You can sort of see the equation there on the side as our best estimate of floor accelerations. And this means that equipment and components in the building that are needed for basic intended function have to be qualified or designed for these demands. Another important aspect is the seismic functional recovery component importance factor, or IPFR, which you can see is part of this equation. And this variable varies according to the functional recovery category, as you can see in the table on the right, and essentially it amplifies the accelerations that need to be used in design. Now, you might be wondering, why does this matter when we're talking about qualifying seismic force resisting systems for functional recovery performance? Well, it matters because FPFR is inversely proportional to RMUFR, which is, again, similar to RMU in AAC 7 Chapter 13. And effectively, this variable reflects the force reduction associated with the structural system ductility. And essentially, we're coming up with values that result in reduced ductility demands. So there's going to be an impact here. Now, theoretically, this is captured in our provisions with the equation that you can also see on the side for RMUFR. But when we develop this qualification procedure for new systems, what we want to do is ensure that the peak floor accelerations associated with the proposed values of RFR and drift limit don't exceed the acceleration demands that are used in the design of non-structural systems. So in a nutshell, our qualification procedure, even though it's centered on the structural analysis of the system, it also tries to capture non-structural systems to ensure they're adequately designed to support the intended functional recovery goals. Okay, so now we're going to go over the qualification procedure for seismic force resisting systems that we followed to develop these, response modification coefficients and allowable drift limits for functional recovery performance, of a range of systems. So essentially the RFR and delta AFR variables that I previously alluded to. In essence, this procedure is intended to be used when developing functional recovery design parameters for new systems that are not yet included in the provision. So it's a standardized framework for functional recovery, similar to FEMA P695, that some of you may be familiar with, which is used to develop R factors for life safety design. So the first step in the qualification procedure is to develop performance groups. So we start with a suite of archetypes, archetype buildings that capture salient features for any given lateral force resisting system. And the intent is that the suite of archetypes is going to capture the variability that we see in design when using these different lateral systems. So for instance, you need to consider variations in height, like low-rise, mid-rise, and high-rise buildings. Another aspect would be to capture differences in component or system design decisions or detailing, to make sure that the impact of these, changes on recovery performance is also captured in the analysis. And I have some examples listed here on the side. So for instance, if you were trying to qualify coupled reinforced concrete shear walls, then when thinking of the coupling beams, you need to consider, the possibility that these may be reinforced conventionally or diagonally. Another example would be, as we'll see later, thinking about brace configurations in a steel concentrically braced frame or a buckling restraint brace frame. Another key point to consider is also the range of gravity systems that are typically used with different seismic force resisting systems, and that's because damage to the gravity system could also trigger safety critical structural damage. So for instance, if we're evaluating a reinforced concrete shear wall, then we need to consider the fact that that shear wall might be coupled with, a steel frame for the gravity system, or maybe a concrete frame, or maybe post-tension flat slab. So we need to consider all these different possible combinations. If we're thinking of a buckling restraint brace frame, maybe this is less of an issue because that system is generally only used with a steel frame for the gravity system. So once we have the suite of archetypes, then we create performance groups by binning archetypes that have similar characteristics. And in our work, all of the systems that we considered have a precedent in the sense that there's a FEMA P695 study. So we've tried to align our choice of archetypes and performance groups with those available in the corresponding FEMA P695 reports. So once we've defined our suite of archetypes, we design each one of them using the functional recovery design spectrum that is shown on the right, which is lower than the spectrum that we currently use in life safety design. So specifically, we designed to what we call the DMAX FRE spectrum, and this is a single spectrum that's intended to represent the most critical site conditions that a system that's designed following prescriptive provisions is going to experience. So it's almost like an envelope, right? That allows us to use this to develop our design recommendations. So when we compare the DMAX spectrum for functional recovery to that used in life safety design, and you see that comparison in the image on the right. So the Dmax for the design earthquake is 2/3 of the risk targeted maximum considered earthquake. And we can see that the Dmax for functional recovery is roughly 75 to 80% of what we use in life safety design. So we then design all of the archetypes using this functional recovery design spectrum. And then what we do is vary some of the variables that I introduced earlier, right? So we're going to look at designs that have different RFR values that go anywhere from 1, so an elastic design, to the R that's used currently in life safety, and allowable drift limits that go anywhere from 0.5% to 2%. And with this later, we'll be able to select appropriate values for each system so that we can minimize the probability of safety critical structural damage. Once these archetypes are designed, we then perform nonlinear analysis for all of the design variations that we're exploring. And the analysis requirements are similar to those in AC 7 Chapter 16. And the goal is to extract key engineering demand parameters. So think of peak story drift, peak residual drift, peak flow accelerations. In certain occasions, depending on the system you're looking at, you might want component-specific demands. And when considering the full archetype space, the modeling and the computational demands you might imagine can be quite high, right? Because you're looking at a lot of possible variations for each possible archetype that you're considering. And for that reason, Appendix A in the NEHR provisions allows the use of simplified analysis methods. And this allowance, again, reflects the fact that many of these systems have already been studied extensively as part of FEMA P695 to develop R factors in life safety design. So we can leverage some of that work to effectively improve, the efficiency of this process. Now, regardless of the approach that is used, the procedure also requires having a peer review team that will need to go over, your choices and then approve the analysis methods. So in our work, we use the Seismic response prediction engine, which was developed by HB Risk, which is one of the partners of the Resilient Design Coalition. And this tool is essentially calibrated to OpenSea's models of systems that were previously used to establish R values in FEMA P695. And it really allowed us to rapidly explore combinations of RFR and drift limits in this design space that I was alluding to. So the figures that you can see on the right show story drift ratios and peak flow accelerations for a sample 8-story reinforced concrete moment frame designed across a range of RFR values and drift limits. So the plots here are showing the results in terms of RFR, but you can easily look at those in terms of drift limit. And as you'd expect, as the design drift limit decreases, then the median story drifts also decrease. And that's something that you can notice in the top figure. And then by contrast, if you think about peak flow accelerations, these are going to become larger as stricter drift limits are imposed. And you can sort of see that trend in the bottom figure. So the next step is to perform a damage assessment using FEMA P58 or equivalent methods. So we only need to consider here structural components, though we do consider both, elements that are part of the seismic force resisting system and the gravity force resisting system, as I was alluding to earlier. Non-structural components are not included in this stage of the analysis, but we'll circle back to the notion of non-structural components and how they're captured in this qualification procedure. So in this step, we're essentially aiming to understand how severe the damage is and how it is distributed throughout the structure for each archetype design variation when it's subjected to the DMAX functional recovery earthquake. So the final analysis step is then to assess functional recovery time using tools like ATC 138, which is an extension of FEMA P58 to evaluate functional recovery time. So under the Appendix A chapter in the upcoming NEHR provisions, the requirement is to evaluate functional recovery time considering only structural damage. And the performance objective is to ensure that the probability of exceeding the target recovery time is less than 10% for functional recovery categories A, B, and C, and less than 15% for D. And as I mentioned earlier, the overall reliability target for the building is 25%. So the intent here is to ensure that only a portion of that allowance is attributed to structural damage. You might be wondering why we're discussing functional recovery time, given that, I've introduced this notion of safety critical structural damage, and this is really what we're actually evaluating, as you can see once again in that fault tree shown on the right. And this is because during the development of Appendix A of the NEHR provisions, we found that safety critical structural damage consistently leads to recovery times that exceed 2 months. So as a result, we can use safety critical structural damage as a proxy for exceeding recovery times ranging anywhere from 0 days to 2 months, which is essentially the target for recovery categories A, B, and C, as I introduced earlier. So when selecting values of RFR and allowable drift limits for a given system so that the functional recovery time targets are met, or equivalently that the probability of safety critical structural damage remains below the specified limits, we can use contour plots like the one that you see here. This is for a sample archetype building. And this, as you can see, helps us identify combinations of RFR and drift limit that satisfy, the criteria. So you see the drift limits that we're exploring in our design space on the y-axis, the RFR values that we're exploring in the x-axis, and then, contours that describe the probability of safety critical structural damage. So in this specific example, if you selected an RFR of 4, combined with a drift limit of 1%, this would be below the 10% probability of safety critical structural damage, which is acceptable to functional recovery categories A, B, and C. And notice, this would be a lot lower, right, than the choice that you would make in life safety design, which for this system would be an R of 8. So reduced ductility demands and stricter drift limits. The challenge is that to determine a set of parameters and whether they're acceptable or not, we're not just looking at a single archetype. We need to consider variability across the entire performance group, right? Which we established in the first step. So to do this, we first compute the average probability of safety critical structural damage across all archetypes in the performance group. And this average, we actually set it to be less than that 10% target for functional recovery categories A, B, and C, and less than 15% for D, so sort of consistent with what I showed in the previous slide, but thinking now as a check on the average. And in addition, because we're focusing on checking the average, we also check a maximum probability of safety critical structural damage across all the archetypes that are part of a performance group. And this is essentially to ensure that even though the average is good, no individual archetype is performing badly. And the maximum probability is actually a little bit more relaxed than the average. So we're looking at 20% as a limit on functional recovery categories A, B, and C, and 25% for D. So the use of both the mean and maximum acceptance criteria was introduced to address concerns that were raised during the development of these provisions for functional recovery performance. In particular, some members of the provisions update committee felt that selecting design parameters for the worst performing archetype would be unnecessarily conservative. So this is why we introduced this approach. So as part of that development process of Appendix A, the Provisions Update Committee also introduced what we refer to as judgment-based caps on the resulting design parameters. So limits effectively on RFR and drift that kind of serve as guardrails for this first generation of functional recovery design provision. So as part of this overall framework, once we've iterated and identified appropriate values of RFR and drift limit from our analysis, those are checked against these judgment-based caps. And specifically, these caps are to limit RFR to be 1 over 1.5 and maximum drift of 1.25%. And for functional, that would be for functional recovery categories A, B, and C. And then the limit for functional recovery D would be R divided by 1.25 and a drift limit of 1.75% for D. So the cap on R is effectively consistent with current practice for risk category 4 designs and risk category 3 designs for functional recovery categories A, B, and C, and D respectively. And the drift limits are similar to those, but slightly relaxed. So the key idea here is that no matter what you get from your analysis, you're never going to relax the RFR and drift limits beyond the values that you see here. Now, I make this analogy of these caps to risk category 4 and 3 designs, but I also want to mention that it's not easy to compare, against existing life safety design provisions. It's not an apples to apples comparison because, as I mentioned earlier, the design ground motions are different, right? The functional recovery earthquake is less than the design earthquake. So even though the precedent of risk category 4 and 3 design is important, it's not a direct comparison to what we're doing here, but these are limits that the Provisions Update Committee still wanted to include. Now, the very last step of this process is to now check our peak floor accelerations to make sure that non-structural component design is adequate. So we compare the peak floor accelerations from our analysis with the accelerations that are actually used to design non-structural components, which are based on the FPFR equations that I previously introduced in part 1. And then essentially, if the accelerations from our analysis are lower than what's used in design, as you would derive from FPFR, then you're good to go. But if the opposite happens and our analysis suggests that we have higher peak floor accelerations, then we need to adjust our mu of FR, which is essentially going to increase the accelerations that we use in design. And this is, again, important because remember, we're introducing lower RFR values. So we're essentially making structures stronger and stiffer, and this can lead to, increased floor acceleration demands. Okay, so now on to part 3. I guess I'll sort of reiterate this notion that we developed this qualification procedure that I'm sharing with you today as part of the NEHRP provisions, because so far we've only developed RFR values and drift limits for a subset of systems in AAC 722. So again, the provisions update committee felt that, we needed a pathway for other systems to be able to be included. And that's why we developed this standardized framework. So what I want to do now that I've talked, a little bit about our approach to functional recovery design and structural non-structural systems, and I've given you a theoretical overview of the qualification procedure, and I want to focus on using BRBFs or buckling restraint brace frames as an example, so you can get a better sense of how this process unfolds. So in AC 722, buckling restraint brace frames have a response modification coefficient R of 8, an overstrength or mega factor of 2.5, and a deflection amplification factor CD of 5. And to capture variability in the design of the system, we're going to consider both buckling restraint brace frames that have moment connections, which sometimes we refer to as having a backup frame, and buckling restraint brace frames with simple connections, so no backup frame. And in this case, we're going to consider using the seismic force resisting system with a steel frame for the gravity force resisting system, which is what's most commonly used when designing BRBFs. So our first step, as you might remember, is to develop performance groups. So remember, the goal here is to create bins that represent distinct structural behavior within the archetype space. And then, this allows us to average results across archetypes that have similar behavior. So the archetype variables that we're considering here in the development of design requirements for BRBFs are the number of stories, the BRB configuration, so thinking about diagonal versus chevron bracing, as you can see in the image in the bottom right. We also consider the number of brace bays per direction, as you can see in the plans on the right. And as I mentioned earlier, whether or not we have a backup frame or not. So whether the beam to column connections in the frame are moment connected or simply connected. We can then delineate performance groups. Again, we're only seeking to delineate or separate, an archetype variable if it significantly affects structural performance. And in this case, the variables that we considered were, of course, the building height, and then the notion of backup frame or no backup frame. So moment connections or simple connections. Other parameters, such as the brace configuration and the number of brace bays, are not delineated into unique performance groups because they didn't drastically alter the global structural performance. And as you can see in this table, this process results in 6 performance groups for this particular seismic force resisting system, 3 of which are moment connected and 3 simply connected, so that you can denote by the M or the S in the performance group definition. And then as a result of this, what we also do is distinctively look at, low, mid, and high-rise structures, and you can see the number of stories that we consider in each one of those groups, and that results in 12 archetypes per performance group, as you can see in the last column of that table. So essentially, to develop these design requirements, we're going to be developing recommendations or checking performance across all these different groups. So for each archetype within a performance group, we create a design space using RFR values that go from 1, so an elastic design, to 8, which is the R value used in life safety design for buckling restraint brace frames, and then drift limits that go anywhere from 0.5 to 2%, which that 2% is the maximum allowable in risk category 2 designs for life safety. Now, for each design variation, we're going to evaluate the nonlinear response at the functional recovery earthquake. And as I mentioned earlier, we used in the study the structural response prediction engine by HB risk. And in the figures here, you can see the resulting story drifts and floor accelerations for designs with a range of RFR values and drift limits considered in this case, an 8-story buckling restraint brace frame that has simple connections chevron bracing, and 2 brace bays per principal direction. And even for this one archetype, remember there are 12 in each performance group. For this one archetype, we have a total of 105 variants, right? Because we're exploring 7 drift limits times 15 possible RFR values. And, I'm not showing them here, but we also calculated residual drifts because, as we'll see later, those were important and had an influence on the safety critical damage probability of buckling restraint brace frames. And if you were exploring other systems like a reinforced concrete shear wall, you would also want to ensure to estimate, couple beam rotations, for instance, to adequately capture damage in those components. So coming back to the BRBF process, so you do the same exercise for every archetype within a performance group, and then, of course, across all of the performance groups. And then these results, or EDPs, are used next in the damage assessment process. So to perform that damage assessment procedure, we need to build what we call a building performance model, which in this case uses only structural components. We only look at structural components when we're adopting this qualification procedure. And for the buckling restraint brace frames, these components include, BRB assemblies, assuming that you have simple connections, BRB assemblies, assuming you have moment connections, bolted shear tab gravity connections, part of the gravity system, column base plates, and welded column splices. And it's important to recognize that sometimes fragilities can change or vary based on, geometry or detailing choices. So in this case, fragilities you'll see later differ based on the BRB to gusset connection. So this is something that would again need to be considered in this step of the assessment. So to use these damage predictions to evaluate safety critical structural damage, we need to map damage states in each component to a corresponding safety class, which will be used when propagating the results through the fault tree that you've now seen a couple of times. So this table provides you with the description and the acceptance criteria threshold for each safety class before triggering safety critical structural damage. So the more severe the damage description, the higher the safety class, and as a result, the lower the acceptance threshold, because we can only tolerate, so many of those components if they're severely damaged. So that's sort of the key idea there. Now, in this example, we're mapping damage states to safety classes for one of the components that we've included in the analysis, in this case, a BRB fragility assembly, assuming simple connections. So these fragilities were developed with funding from Corebrace and actually updated as part of the ATC 138 project to reflect, latest testing and design requirements in AIC 341. So the challenge in this step can be the lack of fragility data, or the fact that maybe there are fragility functions that exist, but they're no longer consistent with the latest design and detailing practices, which was our case here, and why these functions were recently updated as part of that ATC 138 project. Now, once you have those functions, what you need to do is this mapping exercise. So in this specific component, we have 2 damage states, where actually damage state 1 is partitioned to have 3 mutually exclusive conditions. So you can see DS1A, DS1B, and DS1C, and the corresponding probability of occurrence of each one of those is shown in parentheses. And then a DS2, which in this case is the one that varies depending on the detailing of the component. So that's why you see a range of values that needs to be updated depending on the archetype in question. Now, this stage of the process is critical, and you might gather requires a little bit of judgment, because you're trying to determine whether or not damage in the component will result in the loss of lateral and/or vertical load carrying capacity in the component, which you can infer from the damage description. So this is certainly a critical step to engage the peer review team, because if the mapping of damage states to safety classes changes, that could have a significant, impact on the resulting safety critical structural damage probabilities. Okay, as I alluded to in the previous section, for each archetype building, we can then use these contours to identify appropriate values of RFR and drift limits that will give us low probabilities of safety critical structural damage. And again, I want to emphasize that this is a contour for one archetype, right? So this is a contour for the 8-story BRBF with simple connections, chevron bracing, and 2 braced bays. But what we need to do is choose RFR and drift limits, not on an archetype basis, but across the performance group. So what we do is we check 2 criteria that I also previously introduced earlier, but I want to reemphasize here. So the figure on the left shows the results now averaged across the BRBF performance group for mid-rises using simple connections. So every dot in the left plot is actually the average across the 6, 8, and 10-story chevron configuration and diagonal configuration, because that's all part of the same performance group, with both 2 and 4 brace base per principal direction. So that's looking at the average within one of the rows of the table with the performance groups that I showed earlier. So in this figure, we're seeking for RFR and drift limits that give us probability of safety critical structural damage less than 10%, which is the mean criterion for functional recovery categories A, B, and C. Now, the figure on the right shows the maximum probability of safety critical structural damage across all of the archetypes in the performance group, and that's where we're checking the 20% limit, so a slightly relaxed criterion, again, just to ensure that none of the archetypes within the performance group are performing, badly. So to streamline this process, what we can actually try to do is group all this into a single figure as opposed to having to look and do multiple checks across different figures. And essentially all I've done here is isolate the 10% contour from the mean results and isolate the 20% contour from the maximum results, right? So you might gather what we're doing is saying mean results, 10% contour, max results, 20% contour, bring both of those together, and we have an easier way to check, for a combination of RFR and drift limit that passes both criteria. Now, this is still just for one performance group. So what we really ultimately attempted to do here is repeat the exercise across performance groups and bring all of this together. So what you can see here is the overall envelope that we use to come up with design recommendations for this system. So here, anything that's shaded in red is essentially unsatisfactory, and anything that's in white is satisfactory. And you can identify, the mean and the max criteria for each performance group. So you can see in the legend to the right of the figure, the different performance groups that are part of, the BRBFs with simple connections. So this is quite useful. You can identify whether you're looking at the maximum criteria or a specific performance group, just, by identifying the color of the line and then the line type. And then, of course, what we've done is highlighted the controlling envelope to make it easy to then identify appropriate design recommendations. You also see here a horizontal and a vertical dashed line, and those are the judgment-based caps that I alluded to earlier that the Provisions Update Committee wanted to introduce and that need to be considered, right, in providing design recommendations. So in this particular case, we recommended an RFR of 5.5 and a drift limit of 0.75% for BRBFs with simple connections. And I'm not going to show it here, but you would then, repeat this exercise for functional recovery category D, which has relaxed acceptance criteria in relation to functional recovery categories A, B, and C. And what I want to emphasize as I, focus on these design recommendations is that these are considerably lower, right? That when we do for life safety design, where you would use an RFR of 8, and where, for risk category 2 structure, your drift limit would essentially be 2%. So we're really producing designs that are stronger and stiffer with the intent of having reduced ductility demand. So we have a very low probability of safety critical structural damage. So we effectively have, short recovery times, which is the ultimate goal of this new chapter. Now, for any given RFR and drift limit combination, we can actually disaggregate the contribution of different component damage to the overall probability of safety critical structural damage. So going back to that fault tree that I've showed a few times already, we're essentially trying to understand, what is driving that overall safety critical structural damage probability. And here I'm showing the breakdown for designs that have an RFR of 5.5 and the 0.75% drift limit that we selected, for BRBFs with simple connections, and sort of showing the three performance groups that are part of that system. And what you can observe in this case is that actually residual drifts are an important driver of safety critical structural damage for buckling restraint brace frames, a lot more so than damage to the braces or damage to the gravity system. So the final check is now to ensure that design recommendations don't result in excessive floor accelerations. And to do this, we're going to carry out two checks. One is sort of looking at the average accelerations across the height. The other one is looking at the peak. So the first one, what we do is we average peak floor accelerations across the building height based on our analysis results. And we normalize that by the average floor accelerations across the building height that would be predicted by FPFR, which is the equation that we use to determine the forces, right, for the design of non-structural components. Now, the second check that we do, or the second ratio that we compute, is the maximum PFA across the building height from analysis, normalized by the maximum PFA from FPFR. So we check the first ratio against a limit of 1 and the second one against a limit of 1.2. And then if needed, we adjust our MUFR to satisfy these criteria. So for buckling restraint brace frames with simple connections, the baseline RMUFR is 1.56. This is one that you can effectively just derive from the RFR and the overstrength factors you can see in the bottom equation on the right. But because of our analysis, we ended up having to change that to 1.15, primarily because of the first check, right? Because if you look at the image on the right, what you might notice is that the peak accelerations are covered by the FPFR equation, right? It's always larger in the AC7 equation than it is in our analysis. But if you look at the average across the height, our analysis results showcase, higher demand. So that's why we had to make this adjustment. So here are the resulting design requirements for buckling restraint brace frames. The results are summarized in a report that was recently submitted to the Provisions Update Committee as we're going through the final balloting of the 2026 NEHRT provisions. And in a nutshell, but for buckling restraint brace frames with simple connections, the recommended drift limit is controlled by residual drifts, as you saw in that disaggregation plot earlier, primarily due to a limiting restoring or recentering force in the system, and RFR is governed by the judgment-based limit. And in buckling restraint brace frames with moment-resistant connections, the recommended drift limit is controlled by a mix of residual drift demands, which are lower than for the simple connection case, and then structural damage to the BRB frame, in particular damage to the gusset connections as a controlling damage mode. And then the RFR is still governed by the judgment-based limit. So these are the entries that went into the table of RFR and drift limit recommendations for the system in that upcoming Appendix A. So I want to very briefly list the other systems that have been qualified by the Resilient Design Coalition and submitted for inclusion in the upcoming NEHRT recommended provisions. So we've studied dam steel moment frames, and then also conventional steel frames to serve as a little bit of a sanity check or a reference. Buckling restraint brace frames with moment connections and with simple connections, as I showcased in the example today. We looked at speed core coupled and cantilevered walls. We've looked at reinforced concrete coupled and cantilevered walls, again, trying to serve as a little bit of a benchmark or reference for the speed core analysis. Rigid wall flexible diaphragm buildings, these are kind of their own beast because the design process is a little bit different. But I wanted to flag that there as well. Precast hybrid moment frames and conventional RC moment frames. And then the last one we've also considered are concentrically braced frames. So for each one of these systems, there's a report with all the details. And our intention is to make these reports publicly available after completion of this code cycle. And I did allude to a peer review team earlier. So in our case, we had a great peer review team that was composed of Greg Dearline, who's a professor at Stanford, Abby Lau, who's a professor at the University of Colorado Boulder, and Bob Pekelnicki, who's an engineer at Degenkolb. So they really kind of dove into all the details and tried to ensure that as we were presenting the results and making design recommendations, we were adhering to this new qualification procedure in Appendix A of the 2026 NEHRT provisions. So what I presented today is probably new to many of you. So I want to point you to two papers that were recently accepted for publication in Earthquake Spectra, and you can access the accepted versions of these with the QR code that you see on the screen. One focuses on this concept of safety critical structural damage, which is the metric that really has informed the development of provisions for structural systems. And then the other one focuses on our approach to the design of non-structural systems. And we're currently drafting 3 additional papers, one on the qualification procedure that I explained today, and then 2 others that are providing a summary of the design recommendations for that wide range of systems that I just presented that have been recently qualified by the Resilient Design Coalition. I also want to point you to a past webinar in which I provide a summary of the structural, non-structural design requirements in a lot more detail. So it's a whole presentation essentially devoted to part 1 of what I talked about today, and really gives you a sense of what will be coming out in those NEHRT provisions. I also gave a more recent version of this presentation as part of an EFIT lecture at the iStruct just in December, and that was recorded, and I've been told it will be made available on the EFIT website pretty soon. So if you're interested in learning more, I feel that's a good session to look over before going over the material I presented today in detail. So with that, I thank you for your attention, and I'd be happy to open it to questions until I have to run to class.
Thanks a lot, Carlos. Very interesting as usual. If you have any question, please type them in the chat. At the moment, we have 2 questions. So one question and another one with multiple questions. So the first question is, when using the contour plots to select the design parameters, what is the distinction between the category classes and C?
Yeah, that's a great question. So there is no distinction between A, B, and C. There's a distinction between A, B, and C and D. And that is because what we found was that if you have safety critical structural damage, you end up with recovery times that are longer than 2 months. And the recovery time targets for A, B, and C are effectively 0 days, 3 days, and 2 months. So what we decided to do is effectively provide design recommendations that were the same for A, B, and C on the structural side. And then there's a distinction for A, B, and C when it comes to non-structural components. So the IPFR values actually change across those, but the RMUFR and drift limits are the same. So that's a good question.
Okay, thank you. And then there is a set of questions, so I will read them in order. So the first one is, can you provide a few examples of the different building occupancies that are allocated at the different recovery targets?
Yeah, okay, great. So good question. And that's something that I explained in more detail in the other webinar that I was mentioning. But functional recovery category A is 0 days of recovery, immediate recovery. A hospital would be, I think, the most clear example of that. Functional recovery category B is 3 days of recovery. So surprisingly, the one that I think stands out the most is that residential occupancies have been grouped into B. And the idea is that you want to make sure people can go back to their homes as early as possible. So that's something that typically would be a risk category 2 in life safety, and we've actually bumped it to recovery category B. Then for C, now you're looking at 2 months. So an example of that would be thinking of, now thinking of universities or schools And a lot of those choices could obviously be made by the actual building owner, right? So if you run a university, you might choose to upgrade your recovery category for your buildings, but those kind of services are the ones that would fall under C, and then D is effectively things that wouldn't fall in any of the other categories. That's a 6-month recovery target. So I don't know, a cinema, right? Like you don't really need that particular service to be up and running immediately after an earthquake.
Thank you. Okay, so the following question is, can you provide an example of how the repair time is calculated based on structural and non-structural EDPs? Uh,
Okay. So let's unpack this.
no,
So the question
Carlos,
specifically,
I'm aware that you don't have much time, so feel free to
yeah.
keep the answer short and then
Okay.
yeah.
Yeah. So it's effectively, we're doing the calculation as outlined in the ATC 138 methodology, which has a preliminary report that's available online. And the final report is finally coming out very, very soon. We've been in discussion with John Heinz from ATC, and they'll be releasing it there. So you have all the details there, but it's effectively very consistent with what was already done in ATC 138. You look at damage in different components, and then effectively based on that damage extent, you look at the repair activity associated with that damage, and you kind of progress through the building based on that damage to the structure and non-structural elements. And there are nuances because you could do certain things in parallel depending on whether you're looking at certain non-structural systems. But to keep it brief, I'll just point you to that reference.
Okay, thank you. Uh, so another question. Uh, so I'm trying to keep it short. I'm trying to summarize it. So it's essentially the question is about if there are key differences in terms of residual drifts for the two different typologies of BRBs with the simple connections and with the moment connections in the
Yeah.
beam to column joints.
Yeah. So the short answer is I showed a disaggregation of safety critical structural damage for BRBFs with simple connections, and residual drifts drove a lot of those results. If you look at the same results for moment connections, the residual drift is a lot lower in terms of its contribution to safety critical damage. So you have a bit more of a balance between damage to the components and residual drift. And I want to emphasize that residual drift was not an issue for a lot of the systems that we explored, but it's pretty important for buckling restraint brace frames and, for instance, steel concentrically braced frames. So it really mattered there. Other systems, not so much of an issue.
Okay, thank you. Uh, and then we have a couple of questions from Jan. Thank you, Jan. On slide 11, regularity doesn't appear to be a feature in the variables.
That's a great question. So obviously I didn't have time to go over it in detail, but in that Appendix A, we have a lot of restrictions, right, on regularity. So in essence, we didn't need to include them in our design space because you're very limited to what types of irregularities you can introduce vertically or horizontally, right, in your buildings when designing for functional recovery. So in that appendix, if you go through it, you effectively are kind of constrained, and that's why we didn't necessarily need to consider things that the provisions themselves are addressing.
Okay. Uh, uh, Two more questions I will ask Carlos, and then I will let you go. I know that
Yeah, yeah, sounds great.
we are.
I honestly, I'm very surprised that there are so many questions. This is great. I appreciate the engagement.
And then, if you want, I can copy them and send them to you. Possibly there is some good feedback or idea. So another question from Jan on slide 13. Are the high drift ratios at the lower stories due to having the same frame top to bottom? Normally, you would increase the design strength on lower floors. I,
Yeah.
I'm not sure. Yeah.
Great question. I will need to unpack the details. I believe the brace sizes actually change up the height, but in intervals. So maybe for the lower rise structures is the same, but then as you introduce mid and high rise, you start having variation. But it is true that what we saw is some localization of results, and that's why you have larger drifts in the lower stories that you do in the upper stories.
Okay. Thank you. So the last question, sorry for those that asked questions and that we were not able to address them. So are there any additional design criteria other than seismic qualifications and increasing non-structural components PFR value that can be adjusted to decrease the damage to acceleration sensitive non-structural components?
Yeah. So there's a really good list of like good design practices for different types of non-structural systems that are included in the provision. So I think there'll be a lot of useful information that goes beyond this notion of, okay, use, larger design forces and qualify your equipment. So there'll be a lot of useful information there. And, things that come to mind is there are tables that specify um, deflection limits in the rails of an elevator system, like things like that. You find very very detailed stuff in the provision, so that would be an example of that. And then in addition to that, there's this notion of a functional recovery coordinator that really tries to ensure that all of these concepts are actually executed in the field. So there's a lot of other stuff that goes beyond design that's just really about ensuring that things are done in the right way and people are aware of the design intent. So in a nutshell, that's what I would point you to. The provisions should be coming up pretty soon if you're very, very interested in these. We already went through this, what we call a PO ballot, a professional organizations ballot. So a draft of the provisions was already sent to folks at like ACI, AIC, and what have you. So if you're very keen, you can reach out and I can ask if we can share, a draft of the provisions so you can look at some of those.
Okay. So, yeah, I think we need to stop here because so Carlos has to go to give a lecture in a few minutes. So I would like to thank Carlos on behalf of SEGED and on behalf of all the participants and of course from myself.
Yeah.
We
Thank you
close,
for organizing.
yep, we close the seminar here and yeah, thanks a lot everyone.
Thank you. Have a good evening.
Bye.